Training sessions in this group one, and our title is Photo Voicing Accelerated Education Content Generation using Large Vision Models. Basically, this was gotten from the view that Uganda hosts a large number of refugees or asylum seekers, that is up to 1.8 million refugees, according to the sources. So we are review that of creating a system that can ease education to these refugees, and that can ease the teaching pedagogy of the educators. So basically, these refugee areas are experienced with low-end devices and lack of academic resources. And basically, most of the refugees come in when they are not conversant with the available languages used when educating, basically the English language. And so with that, we are of creating a system that is cultural based, is able to generate educative for these refugees, and also create is the educators in generating educative information to students. Basically, these refugee learners come and have limited time to cover a large, maybe a wide number of the curriculum. Basically, let's say an example, a curriculum maybe 4 years, it is covered basically in 2 years, and through the accelerated education program, which is basically at this time is theoretical, this becomes difficult for these refugees to get all the content and maybe get something themselves. And then the view is passing that information from the National Curriculum Development Center and the Accelerated Education Program, passing it into the system so that it is able to create educative content that is relevant to the competence-based curriculum that is available in the country as in for now. Let's have an overview. Basically, the idea is to create a pipeline where artificial intelligence models from Hugging Face, and basically Hugging Face is an open source platform where you get already trained models that just need to be fine-tuned to do a given task. Basically, these models will understand the educational needs and generate plans for the educators. With the use of in-depth tools such as Blender, we shall create visual assets. The model shall be able to create visual assets that are story-based, so that story-based on a particular topic, let's say maybe farming. So the model will be, or the system will be able to create a photo voicing image that is able to elaborate how farming is practiced in the area based on the visual story. Also, we shall use tools like Unity, and this will be used for interactive application for refugee learners, and also used for simulations. So by leveraging large vision models, it's not just generating content, but creating a culturally responsive bridge between standardized education and localized lived experiences. Basically, the computational, the first paper title is Neural or Multimodal Task Retrieval across languages, and basically this has both An abstract, both image caption pairs and translation pairs provide means to learn deep representations and connection between languages. Here we use both types of pairs. The mural, that is the multimodal multitask representation across languages. With multimodal, we mean combining a combination of a number of models, like let's say Lava, Pix to Pix. Those models can be combined into one. That's what we call a multimodal. And basically, what will come out as a result will be a multitasking model. With a dual encoder, that solves two tasks, basically image to text matching, and the second is translation pair matching. And this is by incorporating billions of translation pairs, that is Mural and Align, or a state-of-art dual encoder that has learned from 1.8 billion noisy image text pairs. Our domain-specific problem basically is from the inability of the standard vision language models, these ones that are available, to understand and generate educational content that is culturally and linguistically relevant to the refugee learners in Uganda. So these pre-trained models like CLIP or Align are heavily biased towards the well-resourced languages such as English, meaning this would fail to accurately connect images of local contexts such as those of the Ugandan market. And with descriptions in languages like Swahili, Luganda, and Akoli, this creates a critical barrier to generating accurate localized educational materials. And basically, this is the computational architecture. As you see from the visualization, the diagram, it uses a dual encoder architecture, which is highly efficient with the two separate encoders. That is a vision encoder, and a text encoder, as you see there in the diagram. And basically, the constructive learning objective is that the model is trained to pull the representations of a matching image text pairs. And basically, there is multitasking. Here, the key innovation is training two types of data simultaneously. So the image to text pairs, these are billions of noisy image captions like Align, and text to image translation pairs are billions of parallel sentences across languages. So the architecture allows knowledge from a massive text data to boost performance for languages with a few image text examples. So the paper title 2, that is the mobile visual language model. This is fast, strong, and open vision language assistant for mobile devices, basically. And basically, an abstract is that this mobile visual language model is a competent multimodal vision language. And with multimodal, we mean a combination of a number of models. These are targeted to run on mobile devices. Yeah, these ones basically they combine a multiple number of models, and they make it into a lightweight model that is able to run on low-end mobile devices. And it's amalgamation of merit architecture designs and techniques that are mobile-oriented, and comprises a set of language models at a scale of 1.4 billion and 2.7 billion parameters. These are trained from scratch at a multimodal vision model that is pre-trained in CLIP fashion, cross-modality interaction via efficient projector, and this is evaluated on several typical visual language model benchmarks. Basically, the domain-specific problem. This was overview due to the inability to deploy powerful inability to deploy powerful AI-assisted educational tools low-cost smartphones or tablets available in refugee settlements. So these high-performance models like Lava, GPT-4, these require significant cloud connectivity and a powerful hardware, which is impractical in low bandwidth or remote areas such as Kabongo, Nakibale. So that is overview of the mobile VLM that is suitable for mobile phones. So this is the mobile VLM architecture, the mobile llama, the LDP, the tokenizer, and the vision encoder. So this is the architecture, the computational architecture, and it comprises of small-scale language models. Basically, this is a custom-designed efficient language model that is 1.4 billion or 2.7 billion parameters. This is much smaller than 7 billion parameter models. These are which have ever been used previously. And it also has a pre-trained vision encoder, a pre-trained vision encoder that uses a vision transformer. A vision transformer, this is pre-trained in a clip-like manner to convert images into embeddings efficiently. It also has an efficient projector. This is a lightweight neural network that serves as a bridge to map the visual embeddings from the vision encoder into a semantic space of a small language chip. Basically, from the architecture, we have the architecture optimizations, we have the mobile-oriented techniques, here we have the computational optimizer and the memory efficiency until we reach the model output. The third title is PALI. This is a jointly scaled multilingual image model, and it is basically effective scaling and a flexible task interface enables large language models to excel at many tasks. So that's why we bring the pathways language and image model, that is PALI. This extends the approach to a joint modeling of language and vision. And PALI generates text based on visual and textual inputs. And with this interface, it performs many vision, language, and multimodal tasks in many languages. And basically, PALI is trained on large pre-trained encoder to decoder language models and vision transformer, which allows us to capitalize on their existing capabilities and leverage the substantial costs training them. Basically, the domain-specific problem of which this was due to the limitation of using multiple separate AI models for different education tasks, which were inefficient and would lead to inconsistent results. A comprehensive educational tool that requires unified AI that can seamlessly switch between generating a lesson from an image, answering a student's question about it, and building loud diagram or in the local language. Basically, the computational architecture, this comprises of the vision encoder. This is a massive vision transformer with 4 billion parameters, specifically trained to extract incredibly detailed visual features. And this is much larger than the vision components of almost other models. It also has the text encoder, the text encoder to decoder, which leverages pre-trained large language model like T5 that is already proficient in understanding and generating text across multiple languages. It also has the interface, which is the mode where the model follows a simple visual input, text to output interface, and it takes an image and text prompt. There is joint scaling. which is both the vision and language components that must be scaled up together to achieve optimal performance rather than having a large language model paired with small vision model. As you see in the architecture, basically we shall see a text prompt from a teacher, and from that, a pre-trained text encoder will try to get an output. This is a text of tokens, and here multimodal fusion and the process occurs with the output. The fourth title is the CORA, that is the efficient fine-tuning of quantized large language models. So, CORA is an efficient fine-tuning approach that reduces memory usage enough to fine-tune a 65 billion parameter model on a single 48 gigabyte GPU while reserving full 16-bit fine-tuning task performance. CORA backpropagates the gradients to a frozen 4-bit quantized pre-trained language model into a low-rank adapters. So this quantized low-rank adapter, the CORA, it is quantized, meaning like its precision is reduced so that it fits on lightweight devices. Yeah, its precision it is reduced with which in turn creates just a small change, basically a small change in its capability, just a minor small change in its capability or in its accuracy, but creating at least a large space so that it can fit on small and mobile devices. This is done through quantization. And the model family which we can get is Guanaco. This outperforms all the previous openly released models on the CUNA benchmark, reaching 99.3% of the performance level. Basically, the domain-specific problem, this was due to the inability to customize powerful state-of-the-art vision language models like Lava and PALI4 for the specific niche domain of refugee education in Uganda. And these models are trained on general internet data and they lack knowledge of local context like cultures and curricula. So fine-tuning them traditionally requires expensive high-end GPUs that are far beyond the budget of a typical humanitarian project, locking you out of the achieving truly relevant and accurate assistance. So we were of a view of ROLAD, a quantized low-rank adapter. So this is the computational architecture, which is composed of 4-bit quantization. And here, the weights of a massive pre-trained model are compressed to a 4-bit precision and frozen. This drastically reduces the memory usage so that the model is able to fit on the low-end devices. The low-rank adapters, instead of updating all the 65 billion parameters, the quantized low-rank adapter trains tiny lightweight adapter layers that are injected into the model, and during training, only these adapter parameters are updated. This basically results to a small loss in the quality or accuracy, but creating room or space so that the system is able to fit on small and mobile devices. The fifth paper title we have is the instruction tuning for large language models. Basically, instruction tuning is a crucial technique to enhance the capabilities and controllability of large language models. So instruction tuning is the process of further training large language models consisting of instruction output pairs in supervised fashion, which bridges the gap between text next word prediction objective of large language models and users' objective. Basically, the issue with this is that it involves training a model so that it learns how to follow instructions, and from that instructions, it can give an output. Let's say an educator may instruct the system maybe to create a visual story of a topic maybe about sanitation. This model is trained to follow the instructions by any user. So it will be able to produce an output. Basically, for our idea is a visual story in the form of a narrative image that talks about sanitation. That's it. The problem, basically the main specific problem, was due to the inability of the pre-trained vision language models to reliably follow the complex education instructions needed for creating curriculum-aligned content. So this is basically taught to follow instructions, which was not in the previous models. This is the general pipeline of the instruction tuning, where we will see instruction data set construction, then we go to the instruction tuning. We have the text label. This will be a pair of text to image, maybe text instruction to output pairs. This will be text label in form of instruction to output pairs. Basically, this is the computational architecture, and it builds upon the existing model architectures. Basically, it comprises of the base model. This is a pre-trained large language model or vision language model like Llama or Lava. And here it has large-scale web data. This is billions of web pages. There, it also has training data. This is a data set composed of the instruction to output pairs. And this instruction it can be in the form of natural language task description, and the output is the desired response. So the billions of instruction to output pairs are used in training this model. The training objective, this is a supervised fine-tuning on these pairs. The model learns to map the instruction to the correct output format and content, which is shifting from a general text predictor to an instruction follower. Basically, this is a synthesized abstract. Basically, a unified framework for the deployable multimodal. This is a combination of all the all the 5 models that I've been talking about, and the creation of the effective localized education content for underserved communities requires overcoming significant technical barriers. And this is a novel framework for a deployable multimodal AI assistant. This involves integration of the different models, such as multilingual and multimodal dual encode architecture, that is the MULO. This ensures practical deployment in resource-constrained environment. We also have the mobile visual language model. This one, it is designed to fit on mobile devices, basically the low-end mobile devices in those communities. We also have PALI for tasks demanding high fidelity and complex reasoning. We also have the quantized row rank adapter, that is the crawler, and in the instruction following, this is the one that is trained to follow. That is trained to follow instructions. Basically, a combination of those models will come up with that unified framework. That is a multimodal that will work or will combine all the capabilities of the 5 models into one, and it is able to accomplish a number of tasks, solve a lot of problems. The problem basically is due to core challenges of Uganda's accelerated education program, the linguistic exclusion, where the available models fail to understand the genetic content in mother tongues of refugee learners. We also have technological marginalization. Here, it requires internet. The available models require internet and powerful hardware, which are unavailable in such settlements. We have the contextual irrelevance. This is off-the-shelf education content and is culturally disconnected from learners' lived experiences. Since most of the learners are from different cultures, basically, it is a challenge for them to abide by the cultures in the areas where they have come. So this is the architecture of the multimodal, or the combination of all the available models. One is a cloud-based high-fidelity engine, that is PALI, Flora, and instruction tuning. It handles complex 9-time sensitive content generation tasks for teachers. This is a combination of a number, so it will be handling complex tasks. And on device mobile assistants, we have the mobile PLM and the neural principles. These provide real-time offline AI interaction with students within any app maybe in which the model is deployed. So these are the sources of the papers used in this presentation. Thank you.